Hello and welcome to lecture 25th. So in last lecture we started discussing about compressor cascade and various nomenclatures, and we realized what we have learned from our fundamental, that's what we were discussing about the air angles. We are more interested towards say reality, means we have introduced other angles, like we have introduced the angles, they are known as say incidence angle, deviation angle, camber angle, stagger angle. And what we realize, say our blades, they are being made for particular angles which we have already been calculated with. And because of my inflow condition, it may possible that will not be incident at a design angle, and that will be entering or that will be striking on blade leading edge at other angle, and that's what we have defined as say incidence angle. In line to that, we have realized because of presence of low momentum fluid and because of our viscous effect under adverse pressure gradient, we are having the effect, that's what is giving my flow exit angle to be deviate from the design, and that's what we have defined as a deviation angle. Then we have discussed about the camber angle, that's what we have defined as a tangent drawn from leading edge to camber line and tangent drawn from the trailing edge to the camber line, that's what is making the angle we have defined as a camber angle. And later on with axial direction, what my blade, that's what is making angle, that's what we have defined as a stagger angle. Now in order to go into detail, we need to realize how do we measure or how do we use these aerofoils for our further design process. We have introduced different types of cascade tunnels. So we have discussed about linear cascade tunnel, we have discussed about say annular cascade tunnel, we have discussed about sector annular cascade tunnel. There we have realized these all tunnels, they are having their own importance. If we consider linear cascade tunnel, in which at particular station what aerofoil we are having, that's what will be coming into the consideration for the study. So basically that's what is giving blade to blade informations. Same way near end wall region, that's what is giving idea about the formation of secondary flows. But the limitation we have discussed, that it is not possible to consider the variation of pressure along the span, because we are neglecting or say this is not taking care of your radial equilibrium. But at the same time it has its own benefit, like we have discussed my flow, that's what is happening on the blade or aerofoil, that's what is initially laminar flow. In between at say about 30 to 40% of my chord, my flow will be of say transition nature, and later on downstream of my trailing edge or towards my trailing edge, my flow, that's what is turbulent. So what is happening on that blade surface, that's what is of our interest. Same way, how my pressure it is been distributed on pressure surface and suction surface, that's what is giving me what is my lifting coefficient or CL. And that lift coefficient we have correlated in sense of pressurizing capacity of that particular aerofoil. Now the flow behavior, that's what is changing as we have discussed with the change of incidence angle. So that's what is possible for measurement, or we can realize what is happening in sense of change of CP. Suppose if I consider different geometrical parameters, that also can be studied by using this linear cascade tunnel. Then in order to have understanding of flow three-dimensionality, we are having the options with say annular cascade tunnel. But the problem is, say if we consider particular stage of my compressor, it may be having more number of blades. So in order to do that simulation, I need to have more number of blades to be made. Secondly, in order to test that at the particular boundary condition, my power requirement will be very huge. The size of the tunnel also will be very huge, and that's what is putting constraint in sense of use. But still people, in order to realize the real actual working condition of the engine and the components, they are using as on today also. Now the trend that has come, it is to use sector annular cascade tunnel. That's what is limiting, or that's what is giving the benefit in sense of we are having number of blades required to be considered for study will be lower. At the same time, we can scale our blade as per the requirement. So that's what is giving so much of flexibility in sense of understanding what is happening on my blade surfaces. At the same time, the same three-dimensional blade what we are using for our engines, that can be tested there. So that's what all we were discussing in sense of our cascade tunnels and their use. Now let's try to understand like what all angles we are discussing, how do we realize that for use for our design purpose. So let's take our first, this is what we have discussed in sense of incidence angle. So let's see, this is what we have defined as an incidence angle. So at the leading edge, my flow, that's what will be incident at particular angle. Okay, and that's what is other than the design angle, that's what we have defined as an incidence angle. Okay, now let's try to look at how exactly we need to realize for our actual working condition. So here if you look at, this is what is representing the performance map for single stage compressor. So on x-axis we are having CA by U tip, sometimes people they are using CA by U mean also. So CA is nothing but that's what is my axial velocity, and U tip, that's what is say my peripheral speed at the tip, and that's what is been represented in sense of maybe pressure ratio or pressure rise coefficient. So pressure rise coefficient we are defining as outlet pressure minus inlet pressure divided by half rho u square. Now here somewhere this point, that's what is say point N, we can say that as a design point. So for all components, say mainly suppose if we consider for the compressor, that compressor we are designing for one particular design condition. That's what we can say design speed is 100% speed. That's what is say for particular mass flow rate and my expected pressure rise. So we can say this is what is my design point or design condition. Now if we look at, suppose if we are having this compressor which is having say axial entry, so we can say this is what will be my velocity triangle. So this is what already we have discussed in sense of my axial velocity, peripheral speed, relative velocity. This is what is say my air angle, we can say it's beta 1. Okay, same way at the exit we can say my flow that will be coming out with some bare air angle beta 2 with velocity v2. If we are having our peripheral speed, we can put it here. That's what will be giving me my absolute velocity and my angle alpha 2. And we have our world component, that's what we have defined as CW2. And if we consider our design for the stage is such that my entry and exit, that's what is axial, we can write down my C3 and C1, that's what is same, my alpha 1 and alpha 3, that's what is same. Now let's try to move for this case. Suppose say for the same case I am moving towards say point A. Let's try to understand say point N and we are moving towards point A. When I say I am moving towards point A, we can say I am decreasing my mass flow rate, or we can say if my peripheral speed it is same. Suppose if I consider it is rotating at the same speed, the movement from point N to A is nothing but that's what is representing decrease of my axial velocity. So if we are putting this, that's what is say, this is what is say less than that of my design axial velocity. So if I will be putting this, this is what will be my axial velocity. Since my peripheral speed we have considered to be same, and if I will be joining, that's what is representing, this is what is my velocity triangle. So just try to understand what we have done. We have moved from point N to point A where my axial velocity is lower. Suppose if I consider I am having say second configuration, that's what is say if I will be moving towards point B, that point B is nothing but that's what is representing higher value of my axial velocity or higher mass flow rate. So if I will be putting that in that sense, this is what will be the change of my velocity triangle. Just understand, remember these things, this is what is very important. Here in this case, we know the characteristic of our compressor is with decrease of my mass flow rate, my pressure that will be rising. Now this is what we have represented in sense of my velocity triangle. So if I will be writing here, I have my change of angle from beta 1 to some beta 1 dash. If I am considering I am having say decrease of axial velocity, that's what I am saying. This is what is increase of my incidence angle. Okay. Now same way here, this is what I am writing as say incidence, it is decreasing or decrease of incidence. So let's say like we are now discussing rather changing of angle from beta 1 to beta 1 dash and beta 1 double dash. We are writing that in sense of change of incidence. We can say when I am having my axial velocity, that's what is decreasing. I have my incidence angle, that's what is increasing. When my axial velocity is higher, my incidence angle, that's what is decreasing. In line to that, suppose if we consider say at the exit condition. So same way, because of change of my axial velocity, this is what I will say will be my velocity triangle. Now look at here, if we look carefully, this is what is representing the change of incidence to my blade. Now because of change of my incidence, I will be having the change of outlet angle, and we know at outlet we are defining that in sense of outlet angle say beta 2, or in other language we are defining that as a change of angle, we are defining that as a deviation angle. So suppose this is what is the case for my lower axial velocity. In line to that, I will be putting this for my say higher axial velocity. So this is what is representing the increase of deviation angle because of say decrease of axial velocity, and this is what is representing the decrease of deviation angle. So now here you can understand, like when I say with the performance map, what is happening. So this is what is my design condition. Now let's discuss about the engine. What is happening? Most of the time my engine, that's what is working under off design condition. When I say off design condition, means during my takeoff I am looking for maximum amount of thrust. That's what where my engine that will be rotating or say running at 100% speed. Now as per my thrust requirement, you can understand I need to have higher pressure rise, and that's what is giving me my movement from point A to N to say A. In line to that, when it is flying at the cruise condition, it may be possible that it will be required like pressure rise to be lower, and that lower pressure rise we can say roughly at this moment as a point B. Like the change of my requirement of thrust, that's what is being managed by different ways. One of the way is by managing the mass flow rate through the engine, and second, that's what is by changing the speed or rotational speed of the wheel or rotational speed of my compressor. So here this is what is representing what is happening at the constant speed configuration. So we can say when we are having our constant speed configuration and when we are having decrease and increase of mass flow rate, we are having change of incidence angle and we are having change of deviation angle. Now let's see what we were discussing. Suppose if I consider this is what is representing the different condition. As we discussed, maybe I may be running my engine at the high speed. So you can say this is what is representing this red color one, that's what is representing when I am running my engine at the high speed. And this green color one, that's what is representing when I am running my engine at the low speed. So in line to what we have understood, here if you look at my mass flow rate, that's what is constant. So if this is what is my configuration, we can say still here in this case we are having say increase of my incidence angle when I say I am increasing my peripheral speed. Same way here, this is what we can say my incidence angle, that's what is decreasing. Now if you look at the exit condition, we will be having similar kind of train, because my peripheral speed, that's what is coming to be higher, that's what will be giving me my deviation to be increased when my peripheral speed is increasing. And here in this case, my deviation, that's what is decreasing with the decrease of speed. So you can understand my blade all the time, that's what is working under different flow incidence. It is working at a design incidence condition, it may be working at say increased incidence angle, it may be working at a decreased incidence angle. And because of change of my incidence angle at the entry of my blade, now if you look at the exit also, my flow field, that's what is changing. And that's what is very important. So let's try to understand what all are the impacts of change of this incidence angle. Now we have our fundamentals, that's what is available with us. What we can see here, this is what is representing say change of incidence angle with the change of my CD drag coefficient, and this is what is representing my lift coefficient. So this is what is my characteristics of aerofoils. Now here if you look at, suppose somewhere here I am having some design point. So that's what already I have designed with. Now what happens if I say my incidence, that's what is increasing. So I say this is what is the increase of incidence, say plus 5 plus 10. We can look at, that's what is giving me higher CL. So when I say it is giving higher CL, the meaning is my lift coefficient is rising. Now when we are talking about the aerofoil for particular blade for axial flow compressor, we can say it is increasing my pressure rising capacity. So with increase of my incidence angle, we are having the increase of pressurizing capacity. But there is a limit. Okay, here if you look at somewhere it is written is a stall. So if you move beyond that point for particular incidence angle, we will be having stall of aerofoil, and that's what will lead to increase my drag. Okay, and here if you look at, this is what is representing with increase of my incidence angle, we are having our drag to be increased. That's what we say, we used to say that as a say drag bucket. Okay, now let's look at on the other side when we are having say negative incidence angle. You can see my lift still it is being generated, but it's lower compared to what lift we are expecting. So the meaning is, this is what is giving us idea like my pressure rising capacity of particular aerofoil, that's what is decreasing. Okay, so this is what we need to remember, this is what is very important. And as I told, as aerodynamists, many people they used to say this as a angle of attack, but for our conventional language we are writing that as a incidence angle. Now this is what is representing how my solidity, that's what is changing with say with variation of beta, and this is what is giving me my lift coefficient. So you can understand, if I'll be increasing my solidity, that's what is giving me, say it's an inverse of solidity, that's what we can say it is giving high lifting coefficient. Now the question will come, say what need to be the incidence, or like how do we decide with the incidence and what to do with the incidence, because that's what is very important. Okay, so what it says, when we are having say our aerofoils which are subsonic aerofoils, my incidence that can be varied from plus 5 to minus 5 degree. When we are having transonic or supersonic aerofoils, my incidence, that's what is plus or minus 2 degree. Here we need to realize one thing, as we have discussed, for aerofoils or kinds of aerofoil what we are using for say subsonic application, kind of aerofoil we are using for transonic application, they all have different leading edge thickness. So if we consider for subsonic aerofoils, my leading edge thickness, that's what is slightly higher on side. So if you look at say for NACA 65, or when we are looking for C4 kind of aerofoil, their leading edge are thicker leading edge, and that's what is little insensitive with the change of incidence angle, and that's the reason why this is what is giving us flexibility of variation, or that can tolerate plus or minus 5 degree. Now when we are talking about the transonic aerofoils, my leading edge radius, that's what is smaller, and that's what is very sensitive. We intentionally are looking for leading edge radius to be smaller because we want to have attachment of our shock with the blade, and that's the reason why the leading edge radius, that's what is smaller. So that's the reason why it is very sensitive with the change of incidence angle. Now here in this case, let's see what all will be the changes. Here this is what is representing in sense of CD and CL. Now what is our interest? So here if you look at, this is what is representing my performance map for axial flow compressor. Here if you look at, this is what is representing my non-dimensional speed, we can say 70%, 80%, 100%. This is what is particularly representing my surge line, and in line we are having say mass flow rate, that's what is in sense of non-dimensional form, and this is what is representing my pressure ratio. Now when we are talking about the change of my speed or the change of my axial velocity, this is what is a meaning. So if you look at different speed configuration, my stall mass flow rate, that's what is different. At the same time, for different speed combination and mass flow rate combination, my pressurizing capacity, that's what is different. So it is very important for us to realize what is happening with the change of my mass flow rate and what is happening with the change of our peripheral speed. Here in this case, this is what is representing three different conditions, because we are more interested in sense of total pressure. So here if you look at, this is what is in line to what we have discussed. So here we can say we are having positive incidence angle, negative incidence angle, and this is what is representing the losses. These losses are nothing but the total pressure losses. Okay. Now here if we try to look at, this is what is my condition 1. So we can say this is what is my design condition. Now look at here, this is what it say, I am having my design condition. So suppose say if I say I have designed for some positive incidence angle, my flow will be behaving absolutely fine, and that's what will lead to give you the losses to be lower. Okay. Now what is happening? Suppose if I consider I am increasing my incidence angle. So realize the thing, when I say I am increasing my incidence angle, that means I am changing my axial velocity or I am changing my peripheral speed. So you can say I am decreasing my mass flow rate or axial velocity, or I am increasing my peripheral speed. Under that condition, there is a possibility that your flow will get separated from the suction surface. And when we say there is a separation of my flow from the suction surface, that's what we have defined as a stall. And because of that, if you look at, this is what is my condition 2. What it says, I am going to increase, or say I will be having my losses to be increased. Rather, increase of losses, my performance is more important. We have discussed, we need to have our engine to operate near to this surge line, not exactly very near to surge line or on surge line. If this is what is crossing to the surge line, the engine will go fail. Okay, and that's the reason why this losses, that's what is always very important. Okay, now look at the different conditions. Suppose if I consider, say we are having our incidence angle, that's what is say lower. So this is what is representing negative incidence angle. Under that condition, there may be chances that my flow will get separated from the pressure surface. So for negative incidence, for that also we have extreme. It says when I am moving more towards the negative incidence angle, we will be having more losses, that's what is happening. And those losses are because of your, say, change of incidence angle and because of the flow separation, that's what is happening on my pressure surface. Now this is what is representing when I say I am changing my condition, say my operating condition, say mass flow rate, when I am changing my peripheral speed. So like with the change of other than the design condition, blades will become very sensitive. Okay, so if you look at, this is what we can say, it is my safe operating range. But when I am moving towards the other condition, we are having our operating range, that's what is increasing. So that's what is decreasing in that particular sense. Okay, so this is what is very important for us to understand what is the meaning of change of incidence angle. Now let's try to understand that with say change of Mach number on the surface. So here if you look at, we are having three different conditions. We have our incidence angle to be 0. What is the meaning of that? You can say my alpha 1, if I am talking about the stator, then my blade angle and air angle, they both are same. Similarly, we can say if it is for rotor, we can write down beta 1 equal to beta 1 dash. So this is what is representing my incidence angle to be 0 condition. Now as we have discussed, we can have our incidence angle, that's what is greater than 0. Okay, so the meaning is here we can say my alpha 1, that's what is greater, my beta 1, that's what is greater. Okay, and we can have third condition in which my incidence angle, that's what is say less than 0. So this is what is my configuration. Now let's try to look at what is happening on the suction surface and the pressure surface of our blade. So here in this case, this is what is representing the Mach number distribution on the suction surface and Mach number distribution on say my pressure surface. Sometimes people, they are using Mach number also for the study. Mainly if we are considering the static pressure or the surface static pressure, that's what is giving more detailed understanding. But here for the sake of understanding, let's take this as a Mach number configuration. So here if you look at what we have learned from our fundamentals, that at the initial stage of my blade, say near my leading edge, I will be having the flow acceleration, that's what is happening up to say 10 to 20% of my chord. So we will be having whole lot of acceleration, that's what is happening on the suction surface. And on later part, if you consider, this is what is, we can say it is a diffusing passage, my passage area is diffusing, my flow will get decelerated. So this is what is representing the deceleration process, we can say the decrease of Mach number. So this is what is happening on my suction surface. In line to that, if we consider say on my pressure surface, again at the pressure surface, we will be having some acceleration at the initial stage, that's what is happening, and we will be having some deceleration of the flow. Maybe on the later part of my blade, we will be having constant Mach number kind of configuration. And as we have discussed, this is what is representing my pressurizing capacity of the blade. Okay, so this is what is say my design condition. I say my incidence angle, that's what is say 0. Suppose if I consider say we are having our incidence angle to be say greater than 0. So what will happen? My streamline or my stagnation point, that's what is moving towards the pressure surface. Just look at, this is what is the meaning of positive incidence angle, or we can say my incidence angle, that's what is greater than 0. So we can say here my flow will incident on say towards my pressure surface. If this is what is your case, you can say we are having a whole lot of acceleration or great acceleration, that's what will be happening on the suction surface up to 10 to 15% of chord. So here we are having great acceleration, that's what is happening. And on later part, we will be having the diffusion, that's what is happening. Okay, so it says high suction surface diffusion, that's what is happening on my suction surface. Now here if you look at what is happening on my pressure surface. So if you look at on my pressure surface, we are having the acceleration, that's what is happening, but it is comparatively less when we are comparing 0 incidence case and this case. So here in this case, we are having small acceleration, that's what is happening on my pressure surface, and we will be having nearly constant Mach number or constant pressure rise on my pressure surface. Now, if you compare these two curves, particularly that's what is representing when we are having our incidence angle to be greater than 0, our pressurizing capacity, that's what is increasing. So, if you recall, we have discussed about say performance map for single stage compressor, where we have discussed when we are having our axial velocity, that's what is decreasing, that's what is giving the rise of pressure, and we have discussed that as a positive incidence case. So, this is what is positive incidence case. Now, if we move, suppose if I consider my incidence angle is less than 0, we can say we are having say negative incidence angle, then my stagnation point, that's what will not be at exactly center, but it will be moving towards the suction surface. So, you can say this is what is a place where my flow is getting incident. Okay, so this place we are having the flow incident, that's what is happening. If that's what is your case, we will be having our flow acceleration, that's what is happening on my suction surface. At the same time, grade acceleration, that's what is happening on my pressure surface. And here if you look at, we will be having the distribution of my pressure or Mach number, that's what is coming to be different. And that's what is indicating there is a deterioration in sense of performance or the pressurizing capacity of my blade. Okay. Now, this is what we need to realize. We can say this is what is my pressure surface and this is what is say my suction surface. And now onwards we need to remember the thing, when we are having shifting of our stagnation point towards the pressure surface, that's what we are defining as a positive incidence angle. When my stagnation point, that's what is moving towards the suction surface, we can say that as a negative incidence angle. So, this is what is universally accepted nomenclature. People, they are defining the change of incidence angle with reference to movement of stagnation point. Maybe it is moving on pressure surface or maybe it is moving on the suction surface. And let me show you here, this is what is representing the CP distribution, particularly when we are having say positive incidence angle and negative incidence angle, and we can realize what we are discussing in sense of positive incidence angle. We are having the management or proper management of flow, that's what is happening on my pressure surface as well as on my suction surface. And do not forget all the time, it's the major contribution for pressurizing capacity of any kind of aerofoil what we are using for axial flow compressor, that's what is mainly been depend on what is a surface curvature for the suction surface. Okay, so here when we are having say negative incidence, we can say we are having say deterioration in sense of performance. So let's see what all we have discussed today. So we have started discussing about the incidence angle and we have realized